Hi, my name is Manoj Tulasidas. I'm an associate professor of computer science in the education track at Singapore Management University. My paper is on a new quality metric for k-means clustering based on centroid locations. Let's start with the problem statement. K-means clustering doesn't produce a good quality metric automatically. Why is this important? Which will be the motivation behind this work? There are two reasons. K-selection, which is the process of determining how many clusters to form before actually running the clustering algorithm. And the second one is the possibility of automated, unattended deployments of a k-means clustering platform. Before diving into our metric, let's first briefly look at what's out there. There are some internal proxies for the quality, and there are some classic metrics. And then there are algorithms that solve at least part of the problem, which is the selection of the number of clusters to form. After looking at the state of the art, we will move on to the key ideas, which we will do in two stages. First, a straightforward computation of the chi-square of the centroid locations, and then we will try to extend it to account for the implicit assumptions and requirements of k-means clustering. Finally, we will benchmark our metric against a host of other metrics and wind up this talk with the implications and possible future directions of this work. From a pedagogical perspective, k-means clustering does offer a host of advantages. It is probably the first unsupervised algorithm that we learn and we teach because it's conceptually simple, it's very easy to explain and understand, and there are well-established algorithms and implementations in all sorts of machine learning and statistical packages. The disadvantages, which will be the problem statement, is that there is no good quality measure for a k-means clustering run. In other words, we don't really know why one run or one output is actually better than another run or another output. Because of this lack of quality metric, we cannot decide easily the right number of clusters to form. What's typically used is a subjective method called the elbow method. And again, because of the subjectivity involved, it's not easy to automate k-means algorithm. In a sense, we cannot deploy it without having manual intervention. For instance, how do you handle new data coming in? Looking at the state of the art, there are some internal metrics, which means something that is generated while running the k-means algorithm. You get sum of square errors. One problem with this measure is that it's scale dependent. The variables, the features in k-means clustering, if you express them in different units, obviously you will get a different sum of square errors, and that is not ideal. You can get rid of the scale dependence using the coefficient of determination, r square, which is the fraction of the variance explained by the model. Because it's a fraction, it is scale independent. But both these things have a problem that there is no clear peak. When k tends to maximum number possible, which is the number of observations, r square will tend to 1 and SSE will tend to 0. Then there are classic metrics. There are few of them. Variance ratio criterion, which will turn out to be one of the better ones. It is defined similar to the F statistic in ANOVA. It is the ratio of the between and within sums of squares. So it's a ratio of two variances. The best value for the number of clusters will be the maximum, absolute or local, in the VRC distribution. Then you have information criteria like AIC, Akai-K, and BIC, Bayesian information criteria. Both of them actually try to penalize overfitting BIC more than AIC. It is driven by maximum likelihood estimates. Then we have certain measures like the silhouette width and Davies-Bouldin index and gap statistic with specific properties. Finally, there is an evaluation function, f of k, based on the comparison between a reference kind of distribution and the actual distribution that you get from the model, similar to the gap statistic. So these are different indexes that you have that can quantify the quality of the k-means clustering run. We will compare our metric against these things. Then we have certain algorithms that are specifically designed to address at least one of the problems, the k-selection problem. Projected mean is one idea, PG means, that will project data and the model into a linear subspace, and then it looks for a good fit between those two. And X means is a way of addressing the scalability issues in k-means and can also determine the right number of clusters to form. G means is a statistical test, and it again scans from within a range of k values to find the best possible k. Then there is a combination of index similar to VRC but using multiple indexes, and some probabilistic measures also. All these things are discussed in the paper. but none of them seem to generate a quality metric that we can use directly. So developing the work, now we are talking about the key ideas in this paper. We use z-scores. So what we can do after clustering is that we have the standard deviation of the clusters, that is the within standard deviation, and we can compute the significance of the distance between the population mean and the cluster centroid. We can compute the z-score and then combine them and normalize it by some degree of freedom. So that's what you get, a horrible looking formula there, but let's break it down. So what we have here is the population mean minus the cluster mean divided by the corresponding component of the cluster standard deviation, squared and summed over the number of features. That just means there's a standardized distance, the z-score of the Euclidean distance. And then it is combined for all clusters, but with a weighting factor, number of elements in the cluster divided by n. So it's the weighted average of these z-scores. And then there is a scaling factor, p minus 1 and k. Now we can look at this one and we can see that this computation of the score ignores the correlation between different variables. The right distance to use in that case is the Mahalanobis distance, which takes into account the full covariance matrix of the cluster centroids. What we have is the distance between the cluster centroid and the population mean, the inverse of the covariance matrix, and then this is like the distance between them, but the covariance matrix standing in between here, and then it gets scaled by the number of elements that you have in each cluster. The actual derivation of this is in the paper, and once we have this dm, we can combine them pretty similar to the score, except that instead of the Euclidean distance, what we are using is actually the Mahalanobis distance, d sub m. And again, you will see that there is this factor n coming here and n sub k from the definition of d sub m. So that means this summation is also like a weighted average. Out here what we have is the normalization factor, the number of degrees of freedom. We have p features, so p minus 1 because we have one mean computation binding them, so p minus 1. And then we have k such centroids. K times p minus 1 is the total number of degrees of freedom of the chi-square. That is actually the sum of individual chi-square distributions for each one of the centroids. So that is actually the reduced chi-square, because it's chi-square divided by the number of degrees of freedom, but with this extra factor of n. So but that is just a scaling factor. So this is reduced chi-square, and this is what becomes a critical part of our new metric. Now, in order to go from the reduced chi-square to the new metric, let's look at the implicit assumptions of k-means algorithm. One is about the membership, and the second one is about variance, the uniformity of these two entities. If the two clusters have vastly different numbers of members in them, the smaller one tends to eat into the larger one. Similarly, if the variance is very different in such a way that one cluster, the blue cluster here, is much tighter than the red one, then the blue cluster will scavenge members from the red cluster. So this is the data that went into it. First of all, if you have balanced clusters, generated 1000 elements each in two clusters with equal standard deviations at two different points, and they get reconstructed very accurately. K-means clustering, we have 1000 members each, and the centroids also are at the right points. But if you have unequal members, so everything is the same as the balanced clusters, except that I changed the number of members in one of them to be 50 as opposed to 1000, and suddenly about 170 members of the larger cluster went into the smaller one. And going back to the same number of members, but this time changing the variance such that one cluster is much tighter than the other one. Again, the tighter cluster takes about 10% of the more spread out cluster. In other words, k-means clustering will work best when the clusters in the real data are balanced. So that points to some quality of the k-means run. In other words, if a k-means run results in balanced clusters, that is likely to be probably a more accurate one. So how do you quantify a lack of uniformity? Let's take a look at the membership first. Ideally, if you have k clusters out of n data points, the membership should have been nk hat, which is n divided by k. The actual one that you get is n sub k. Now, if you can find a standard error and a z-score, then you can combine them. So standard error turns out to be the square root of n divided by k. Again, the derivation of that is in the paper. And z-score is obviously just the difference in the in what is measured and what is expected, divided by the standard deviation, and then you combine them for the k clusters by taking the square of the z-score. So you get one measure of the unequal membership. Similarly, for unequal variance, we can define the ideal variance and a standard error. Ideal variance turns out to be the sum of square errors divided by n minus k this time. A standard error on the variance, that turns out to be that. This comes from a reference from the paper. And the actual variance is the within standard deviation, which you can define by summing over the data points in each cluster. So this inner parenthesis here is the data point minus the cluster centroid squared and summed over the number of features that we have, and summed over all data points, but limiting the summation only when the cluster affiliation is k. And then you divide by the number of elements in the cluster minus 1, that is the normalization for our variance. You have a measured within standard deviation and an ideal one. Again, you can compute z-score, square them and sum them up to get a measure of unequal variance, its effect. So now we have three entities. One is the reduced chi-square, and then something like combines z-score coming from the lack of uniformity in the number of members and lack of uniformity in the variance. How do you combine these things? We want high reduced chi-square so that the clusters are distinct, and we want low lack of uniformity, those things. So we kind of came up with a heuristic definition and called it covariant metric. We called the ratio between the chi-square and the sum of the measures of the lack of uniformity. Let's test it on synthetic data as well as real data. Synthetic data is generated using cluster generation in R with parameters, number of clusters running from 5 to 20, a number of variables running from 2 to 32, and a suppression index specific to this package running from 0.34, which means high suppression, to 0.01, which is expected to be realistic kind of clusters. Then we have constants for noisy variables, outliers, etc., which we set to 0, and we set the cluster membership to be equal, and then we had a range for the variance also. Then we have real data, 3 of them from the UCI datasets, standard datasets, iris, wine, and seeds, and 1 a private dataset coming from a survey of 127 students, male and female, so 2 classes, and 4 variables: height, weight, length of hair, and age. How do we actually do the comparison between a new metric and existing metrics? Because the new metric as well as the existing metrics might give you the right number of clusters. Even then we might want to say that one is better than the other. We base it on the curvature of the peak. If a peak is highly defined, well defined, then the curvature will be high. That is actually just the second derivative in the case of continuous functions. So this is just a 3-point measurement of the second derivative. We can actually translate that in the case of discrete measurements. So what we do is to look at the wings and take the difference between the wings and the peak divided by the average value of the wings. That will give you how significant the peak is, and this is identical to the second derivative. Gamma turns out to be a dimensionless proportional to the second derivative at the peak. In order to prove to you that it is actually a good measure, let's look at a normal distribution where we vary the standard deviation running from very close to 0 all the way to 2, and gamma on the y-axis, notice that is actually logarithmic scale, and we can see as we reduce sigma, which means as we make the peak better and better defined, the gamma shoots up. So using all these things, the accuracy, which is the fraction of the time we actually get the same number of reconstructed k as the number generator, and gamma, which defines how significant the peak is, we get a bunch of numbers for R index on top. For well-separated clusters, we get 100% of accuracy. For realistic clusters, we get only 45%. But our peaks are always quite well defined. And looking at other indices, VRC does extremely well in terms of accuracy. 100% for well-separated, 60% for realistic. But its peak is typically not that well defined. So it might be difficult to actually detect a peak, or the peak might shift statistically. There are other indexes like Davis-Boulder index does extremely well for realistic 85% of the time, but the peak also is very small. The takeaway from here is that our metric shows very sharp peaks, but VRC actually does perform better. So these are some cases where we can see the last column here is where both VRC and our metric, they did find the right number of clusters, K, is equal to the number of generator clusters. So look at the peak. It's much sharper for the covariant metric. Now, going over to real data, the covariant metric does extremely well in all 4 data sets, while all other metrics seem to fail, at least for one of them. So covariant metric reconstructed the right number of classes for iris, young adult, 2, male and female, wine and seeds, also with very sharp peaks, especially for young adult and seeds, and reasonably good peaks for wine and iris also. BRC did reconstruct young adult, wine and seeds, but with much shallower peaks. BIC and AIC are not very good. GAP does well for 3 of them, but it has a problem that is computationally very, very inefficient. So just to show you how well our peaks are in covariant metric, we can see that for iris data, the peak is quite well defined, and young adult data set is much better, and wine data set also is quite nice, and seeds data set also shows a nice peak. So it seems to work in all data sets that we tried so far. So that brings us to the end of the talk, the last slide, the limitations and the conclusions. On the limitations column, we did not do any pre-processing of the data because we are trying to deploy this in an unattended fashion. Second point is that the conceptual mathematical validity of a metric as a ratio is on shaky grounds, really. We have 2 measures of lack of uniformity. Are we supposed to give them equal weightage or give them different weightage? We don't know, really. Finally, there is an idea that maybe combining the sharpness of the peak with the metric itself may improve the accuracy. The extension from reduced chi-square to the covariant metric obviously assumed balanced clusters, but this may not be practicable in automated kind of deployments where new data is coming in. There's no guarantee that the clusters are supposed to be equal in terms of membership. So the future direction is to actually develop an algorithm that might be more appropriate for unattended automated kind of insight generation using k-means algorithm. Concluding, the proposed metric seems to work extremely well in real data, beating all of the metrics. On synthetic data, it's a different story. VRC is actually better, but VRC is poorer in terms of the sharpness of the peaks. And in any case, either VRC or the covariant metric can easily replace the subjective elbow method that we teach our students. Among the other metrics, GAP is pretty good and also is computationally very, very expensive. Another takeaway is that the information criteria like AIC and BIC, they are very bad. Finally, if further studies show that the covariant metric is very good, that will imply that k-means can be automatically optimized, which means it can be deployed in unattended kind of situation where it will generate insights from data automatically, which of course is the gold standard for data analytics. Thank you, and address any questions to my email, please.